Domingo Toledo Alamo, 1945 to 2025 by Carlson and Rossi. I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here, and I'm reading this obituary which was published in the Notices of the AMS in 2026. Domingo Toledo, 1945 to 2025, made lasting contributions to differential geometry, complex analysis, and topology. His work connected algebraic and analytic methods in the study of complex manifolds, locally symmetric spaces, and fundamental groups of Kähler manifolds. He was known for the precision of his arguments and his ability to connect abstract theory with concrete geometric constructions. Toledo earned his PhD from Cornell University in 1972 under James Eales and Roger Livesey, writing a dissertation on the Atiyah-Bott fixed-point formula. After appointments at Princeton and Columbia, he joined the University of Utah, where he remained for the rest of his career. His early papers revealed a geometric sensibility shaped by the tools of algebraic topology and differential geometry. Over time, he built a framework linking harmonic maps, Kähler geometry, and the topology of manifolds with additional geometric structure. Toledo-Tong theory. A major strand of Toledo's work in the 1970s, done jointly with Larry Tong, centered on analytic and homological foundations of the Riemann-Roch theorem for complex analytic spaces. Their papers, including a parametrics for boundary bar and Riemann-Roch in Czech theory, 1976, constructed explicit chain-level realizations of characteristic classes and direct image maps for coherent sheaves. The central idea was that a coherent sheaf on a complex manifold can be locally resolved by free modules on small Stein neighborhoods, and that these local resolutions are quasi-isomorphic on overlaps. Toledo and Tong showed how to glue these complexes coherently by constructing an infinitely compatible system of homotopies, replacing abstract injective resolutions with explicit geometric data. This led to a Czech theoretic model of the derived category suitable for analytic geometry. Their results provided Riemann-Roch identities for complex analytic manifolds without recourse to algebraic methods, a major step beyond what was then known for smooth projective varieties. In contrast with the approach of Atiyah and Singer, who used Riemannian metrics and elliptic operator theory, Toledo and Tong's constructions were purely holomorphic and invariant under biholomorphisms. They allowed local computations to be glued globally, and in this way offered the first analytic, coordinate-free proof of Riemann-Roch type theorems on general complex manifolds. Their techniques have since found applications to orbifolds and higher stacks. Kähler groups and harmonic maps. Around 1980, Toledo began a second major line of research, motivated by questions about the topology of Kähler manifolds and the nature of their fundamental groups. A finitely presented group is called Kähler if it arises as the fundamental group of a compact Kähler manifold. These groups form a rigid subclass of all finitely presented groups constrained by Hodge theory and harmonic map techniques. Toledo made pioneering use of harmonic maps between Riemannian manifolds to study these questions. In particular, he investigated when the fundamental group of a locally symmetric space can be realized as a Kähler group. One of his early results showed that the fundamental group of a real hyperbolic manifold of dimension at least 3 cannot be a Kähler group. The argument relied on analyzing harmonic maps from Kähler manifolds to negatively curved targets and the behavior of their energy functionals. This line of reasoning later became a standard tool in the study of rigidity and representation varieties. Toledo's 1993 paper in Publications Mathématiques de la HES constructed the first explicit examples of compact complex projective varieties with non-residually finite fundamental groups, answering a question posed by Serre. The examples were obtained by combining techniques from harmonic map theory and complex hyperbolic geometry, demonstrating the power of analytic methods in addressing group theoretic problems. Moduli spaces and period mappings. Toledo's later research focused on the variation of geometric structures into the geometry of moduli spaces. With collaborators including James Carlson, Daniel Alcock, and Anton Domik, he studied period mappings and their relationships with locally symmetric spaces. In joint work with Carlson and Alcock, he examined cyclic covers of complex projective spaces and the associated variations of Hodge structure. A notable result was their identification of the moduli space of cubic surfaces with a discrete quotient of the complex 4-ball. The idea was to use the period map for triple covers of projective three spaces branched along a cubic surface. The associated space of cyclic Hodge structures is four-dimensional, just as is the moduli space of cubic surfaces. A computation of the differentials showed that the period map has full rank, and a global argument confirmed that the map is an isomorphism. This result parallels the classical identification of the moduli space of cubic curves with a quotient of the upper half-plane by a subgroup of SL2Z. These investigations blended explicit calculation with broad geometric perspective, linking algebraic geometry, Hodge theory, and discrete groups. They illustrated Toledo's characteristic approach, analyzing deep questions through concrete examples worked out in detail. The Toledo invariant. A unifying concept across Toledo's later work is the Toledo invariant, introduced in his 1989 paper, Representations of Surface Groups in Complex Hyperbolic Space. Given a representation of the fundamental group of a closed orbit-oriented surface into a Lie group G of Hermitian type, the symmetric space G mod K admits a canonical Kähler form. The Toledo invariant of the representation is defined by integrating the pullback of this form over the surface. It provides a numerical measure of how the representation interacts with the Kähler geometry of the target. In collaboration with Anton Domingo, Toledo established a bound for this invariant, generalizing the classical Milnor-Wood inequality. The bound depends on the rank of the symmetric space and the Euler characteristic of the surface. When equality holds, the representation exhibits rigidity. The corresponding point in the character variety lies in a component of smaller than expected dimension. This phenomenon connects geometric structures on surfaces with bounded cohomology and stability properties of Higgs bundles. The Toledo invariant became central to later developments in higher Teichmuller theory, where representations with maximal Toledo invariant define special components of the representation variety, often parameterizing geometric structures on the surface. These ideas influenced the subsequent work of Corlett, Simpson, and many others, linking harmonic maps, non-abelian Hodge theory, and the topology of moduli spaces. Later collaborations and extensions. In the 2000s, Toledo collaborated with Oscar Garcia Prada, Olivier Bicard, and Brian Collier to extend the concept of the Toledo invariant and the Milnor-Wood inequality to higher dimensional and Hodge theoretic contexts. Their 2011 and 2017 papers analyzed representations of the fundamental groups of compact complex hyperbolic manifolds into isometry groups of quaternionic hyperbolic space, proving that equality and the corresponding inequality characterizes totally geodesic representations. Using the theory of prehomogeneous vector spaces, they generalized the notion of the Toledo invariant to representations associated to arbitrary z-gratings of complex semi-simple Lie algebras. The Hermitian case corresponds to a three-term grading. The general framework gave new rigidity results and provided foundations for studying the topology of moduli spaces of Hodge bundles and Higgs bundles. Influence and style. Toledo's mathematics was characterized by precision, clarity, and geometric intuition. He worked comfortably across algebraic and analytic boundaries, translating cohomological constructions into concrete geometric models. His results often connected apparently separate theories, Riemann-Roch and Čech cohomology, harmonic maps and Kähler groups, Hodge theory and discrete group actions that reveal a coherent structure behind them. The analytic viewpoint he developed with Tong and later extended to harmonic maps provided tools that remain central to modern complex geometry. Toledo's influence extended through collaborators and students who absorbed his method, beginning with concrete examples, constructing explicit analytic models, and using them to prove general theorems. The techniques of the Toledo-Tong theory and the concept of the Toledo invariant both continue to play important roles in complex and differential geometry. Oh, that's a very interesting article. The guy had his fingers in a lot of pies. Yeah, not much I can add about this. Very inspiring. I'm always very inspired when I read these memorial tributes in the notices. It always encourages and inspires me to try to be a better mathematician myself. I'm Dr. Samuel Allen Alexander, mathematician and philosopher. Please like, comment, and subscribe. I'll see you in the next video.